Can you believe it? A colossal ice slab, 7 miles in diameter and a mind-bending 7 billion years old, older than Earth itself, just came screaming into our solar system at a staggering 130,000 miles per hour. This isn't just another space rock. This is primordial water ice, preserved in the cosmic deep freeze since before our sun was even born. We are about to witness the awakening of an ancient comet, examine ice from alien star systems, and decode messages written in starlight from the early galaxy. But we have just months before it vanishes forever behind our sun. Hit that like button and subscribe because you won't want to miss this cosmic time capsule. Prepare yourselves. We begin. Welcome to the Astronomy Library. The telescope in Chile was doing what it does every clear night, scanning the southern sky, when everything changed forever. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System Atlas was performing a routine survey for dangerous space rocks. Just another clear night of scanning the cosmic neighborhood. The automated system captured thousands of images, processing them through algorithms designed to spot anything moving against the background stars. Most nights, it finds asteroids, sometimes comets. But this night, it found something that shouldn't exist. The object appeared as a faint dot, barely visible against the dense star fields near the galactic center. It was like finding a single firefly in a stadium full of Christmas lights. But what made astronomers stop and stare wasn't how it looked, it was how it moved. This thing was racing across the sky faster than anything they'd seen before, covering distances that would take normal solar system objects weeks to cross. Within hours, observatories around the world were turning their instruments toward this mysterious visitor. The Zwicky Transient Facility in California found it in their archives. The Canada-France-Hawaii telescope spotted its faint glow. Each new observation confirmed what astronomers were starting to suspect, but hardly dared to believe. This wasn't just another asteroid tumbling through space. The trajectory calculations showed something extraordinary. The object was following a hyperbolic orbit, meaning it would never loop back around our sun. It was passing through our solar system like a cosmic tourist, here for a brief visit before continuing its journey into the infinite dark. The Discovery team initially gave it a temporary designation, 11PL3Z, a cryptic codename for what would soon become one of the most important astronomical discoveries of the decade. As more telescopes joined the hunt, the evidence became undeniable. This object had traveled between the stars for millions, possibly billions of years, before stumbling into our neighborhood. The Minor Planet Center, the official authority for cataloging cosmic visitors, needed just 24 hours to make it official. On July 2nd, they announced the confirmation. Humanity had found its third known interstellar object. The designation changed from that cryptic code to something far more significant. 3. Atlas. The 3 marking it as the third interstellar visitor we'd ever detected. Think about that for a moment. In all of human history, we've confirmed exactly 3 objects that originated beyond our solar system. This cosmic messenger joined the legendary ranks of Oumuamua and Borisov. Yet, even among these rare visitors, this new arrival would prove to be different, special, and ancient. The discovery was just the beginning of the story, but what the telescopes revealed next would challenge everything. We thought we knew about the age and composition of interstellar space. This cosmic visitor almost slipped through our fingers, completely unnoticed. Amateur astronomer Sam Dean was digging through telescope archives when he made a startling discovery. The object we now call 3I Atlas had been hiding in plain sight for weeks, captured in images dating back to June 14th. Why did it take so long to spot? Picture trying to find a moving star in the most crowded part of the night sky. The object was traveling directly in front of the galactic center, where millions of stars create a brilliant backdrop of cosmic confusion. The dense star fields of Sagittarius had provided perfect camouflage for this interstellar intruder. Every image showed countless points of light, making it nearly impossible for automated systems to distinguish between distant stars and this nearby visitor. The discovery algorithms kept dismissing it as background noise. Time was running out faster than anyone realized. Unlike asteroids that hang around our solar system for millions of years, interstellar objects are cosmic sprinters. They raced through our neighborhood at breakneck speeds, visible for just months before disappearing forever. The situation grew more urgent when astronomers calculated the viewing window. This object would remain observable from Earth only until September, when it would pass too close to the Sun to study safely. That gave the global astronomy community roughly 10 weeks to unlock the secrets of a visitor that had traveled between the stars for eons. Observatories worldwide launched into action like a coordinated emergency response. The Hubble Space Telescope cleared its schedule. The James Webb Space Telescope prepared infrared observations. Ground-based telescopes from Chile to Hawaii began round-the-clock monitoring. Every clear night became precious. The European Southern Observatory deployed their very large telescope array for massive mirrors working in perfect synchronization, creating the equivalent of a single telescope 25 meters across. In Japan, the Subaru telescope joined the hunt. In Spain, the Gran Telescopio Canarias turned its 10-meter mirror toward the mysterious visitor. Even citizen scientists joined the race. The Unistellar Network, made up of hundreds of small telescopes operated by amateur astronomers, began tracking the object. Despite using instruments just 3 to 4 inches across, these dedicated observers successfully captured images by stacking multiple exposures together. The clock was ticking in more ways than one. Not only would the object soon vanish behind our sun, but its distance from Earth was constantly increasing. Every day that passed meant dimmer images and fewer photons reaching our detectors, like trying to photograph a candle that's being carried farther away every second. The astronomical community had stumbled upon a cosmic time capsule, and they had just weeks to decode its ancient secrets. What they discovered about its incredible size and speed would reveal clues about an unimaginably violent cosmic event that launched this visitor toward us. 7 miles of ancient ice and rock were hurtling toward our inner solar system. When the Vera Rubin Observatory analyzed their archived images, they uncovered something astronomers hadn't expected. Hidden in photographs taken on June 21st, before anyone knew to look for it, lay clear evidence of this object's true scale. The images revealed a nucleus roughly 7 miles across, making it a genuine giant among interstellar visitors. To put that in perspective, imagine Manhattan Island carved out of primordial ice and rock, then hurled between the stars for billions of years. The sheer scale was breathtaking. The previous interstellar visitors were cosmic pebbles by comparison. Oumuamua, the first confirmed interstellar visitor, was a cigar-shaped object stretching just 400 meters, about the length of 4 football fields. 2 years later, Borisov, the second confirmed visitor, measured less than a mile across. This new arrival dwarfed them both. The size revelation came from careful analysis of the object's brightness and the way sunlight scattered off its surface, like forensic investigators reconstructing a crime scene from tiny clues. Astronomers used photometry to determine the dimensions of something 400 million miles away. The calculations showed a nucleus with a radius of 3.5 miles, with a margin of error of just 0.4 miles. Size matters in the cosmic realm, and this discovery changed everything. Larger objects retain their internal heat longer, keeping volatile compounds like water, ice, carbon dioxide, and methane locked away in frozen storage for eons. A 7-mile-wide comet could preserve materials from its birth star system virtually unchanged, creating a natural time capsule of ancient chemistry. But the size wasn't the only surprise hiding in those archived images. The data revealed something even more intriguing. The object was already showing signs of activity, while still incredibly far from the sun. A faint coma of gas and dust surrounded the nucleus, proof that this ancient visitor was beginning to come alive for the first time in billions of years. Most comets from our own solar system remain dormant until they get much closer to our star. This object was releasing material while still beyond the orbit of Jupiter, suggesting it contained highly volatile compounds that sublimate at extremely low temperatures, like a deep freeze that had been unplugged after 7 billion years of storage. The discovery team realized they were looking at something unprecedented. Previous interstellar objects had been studied only as they raced away from our sun, already depleted of their most interesting materials. This time, astronomers were catching an ancient comet in the act of awakening, watching as billions of years of accumulated ice began transforming directly from solid to vapor. The size revelation promised even more dramatic developments as this cosmic giant continued its approach toward the inner solar system. The real question wasn't how big it was, but how fast something this massive could possibly be moving through space. At 130,000 miles per hour, and still accelerating. This ancient visitor was moving faster than anything astronomers had ever tracked in our solar system. To understand just how impossibly fast that is, imagine a bullet that could travel from New York to Los Angeles in less than 90 seconds. That's the kind of velocity we're dealing with when we talk about interstellar objects. The speed measurements came from carefully tracking the object's position against background stars over several nights. Like cosmic radar, astronomers used the Doppler effect to measure how quickly it was approaching us. The radial velocity reached 61 kilometers per second, fast enough to escape the gravitational pull of our entire galaxy. If it were pointed in the right direction, this wasn't just fast for a comet. This was fast for anything. The space shuttles reached their maximum velocity at just 5 miles per second during orbit. The fastest human-made object, the Parker Solar Probe, tops out at 430,000 miles per hour when diving close to the Sun. This interstellar comet was moving at nearly a third of that speed without any help from rocket engines or gravitational slingshots. What could accelerate a 7-mile-wide chunk of ice and rock to such incredible velocities? The answer lies in one of the most violent events the universe can produce: stellar encounters. When this object was still part of another star system billions of years ago, something catastrophic happened. Perhaps two stars passed unusually close together, their combined gravitational fields acting like a cosmic catapult. Or maybe a massive planet migrated inward, disturbing the outer reaches of its system and flinging countless comets into the void. The ejection process requires precise conditions, to little velocity, and the object never escapes its home system. Too much, and it gets torn apart by tidal forces. This visitor hit the cosmic sweet spot, receiving just enough energy to break free, while remaining intact for its billion-year journey through interstellar space. As it continued approaching our Sun, the gravitational acceleration would increase its speed even more. By the time it reached its closest approach in late October, it would be screaming through space at over 200,000 miles per hour, fast enough to cross the entire continental United States in just 55 seconds. The hyperbolic trajectory told astronomers this object would never slow down enough to be captured by our Sun's gravity. Like a marble rolling down a curved ramp, it would sweep through our solar system once and continue into the cosmic dark forever. This was a one-time-only performance, a brief cosmic concert that would never be repeated. The speed also created technical challenges for observation. Telescopes had to track the object's rapid motion across the sky, constantly adjusting their pointing to keep it in view, like trying to photograph a race car from the grandstands. The tracking systems worked overtime to capture clear images of this fast-moving target. These incredible velocities held clues to something even more remarkable: the object's mind-bending age, 7 billion years old. This cosmic wanderer predates our entire solar system by 3 billion years. University of Oxford astronomer Matthew Hopkins ran the calculations multiple times, hardly believing the results, using computer simulations to trace the object's trajectory backward through galactic history. His team discovered something extraordinary. This visitor likely formed when the universe was less than half its current age, during an epoch when the Milky Way looked completely different. Think about that timeline for a moment. When this comet first condensed from the disk of gas and dust around an ancient star, Earth didn't exist. Our Sun was still just a cloud of hydrogen floating in space. The entire solar system was nothing more than raw materials scattered through an unremarkable patch of the galaxy. Yet, this object was already fully formed, beginning its billion-year journey through the cosmic void. The age calculation came from analyzing the object's steep trajectory through our galaxy. Unlike previous interstellar visitors that traveled roughly parallel to the galactic plane, this one approached from a sharp angle, suggesting it originated from the Milky Way's thick disk. This region contains the galaxy's oldest stellar populations, ancient suns that formed when the universe was young and metal-poor. Stars in the thick disk are typically 7 to 10 billion years old, making them senior citizens compared to our 4.6 billion-year-old Sun. The planetary systems that formed around these ancient stars would have created comets from primordial materials that have remained virtually unchanged since the early universe. This visitor represents a frozen sample of chemistry from when the galaxy was still in its cosmic infancy. The implications are staggering. Every molecule of water ice in this comet condensed from vapor in another star system, when the universe contained far fewer heavy elements. The carbon compounds, silicate dust, and organic molecules all formed under conditions that no longer exist anywhere in the local galaxy. This is literally a piece of the ancient cosmos, preserved in perfect condition by the cold of interstellar space. Hopkins and his team used something called the Otto-Hoxford model to predict the most likely origins of interstellar objects. The statistical analysis suggested a 2/3 probability that this comet is older than our solar system. Among all the interstellar visitors they could potentially discover, this one ranks as the most ancient they're likely to encounter. The age estimate also explained the object's unusual composition. Spectroscopic observations were already revealing water ice signatures, exactly what the model predicted for a comet that formed around an old metal poor star. Ancient stellar systems produced ice comets because they lacked the heavy elements needed to create rocky planets close to their stars. This wasn't just another space rock passing through our neighborhood. This was archaeological evidence from the early galaxy, a witness to cosmic events that happened when the universe was young. Every observation was like reading pages from a history book written in ice and stone. The ancient age raised an even more intriguing question. Where exactly in the galaxy had this cosmic time capsule spent the last several billion years? The trajectory analysis revealed something unprecedented in the study of interstellar objects. While previous visitors, like Oumuamua and Borisov, traveled roughly parallel to the main disk of our galaxy, this comet approached from a steep angle that cuts through multiple galactic layers. Like a cosmic elevator moving between floors, it traveled from the thick disk down into our local neighborhood in the thin disk. The thick disk represents the Milky Way's ancient history made visible. This comet may have spent billions of years in the galactic equivalent of cosmic rural areas, rarely coming close to another star system. The implications for astrobiology are fascinating. If this object formed around an ancient star, it carries information about planetary formation processes that occurred when the galaxy was chemically primitive. Asterisk. The thick disk origins promise to reveal something even more remarkable: pristine water ice that had been frozen since before Earth existed. 7 billion-year-old water ice preserved in perfect cosmic cold storage was about to tell us secrets about alien star systems. Spectroscopic observations from the Gemini South Telescope and NASA's Infrared Telescope facility revealed something extraordinary hiding within the comet's growing coma. The light signature showed clear evidence of water ice sublimating directly from solid to vapor, creating the ghostly atmosphere surrounding this ancient visitor. This wasn't just any water ice. This was H2O that condensed around another star when the universe was half its current age. Think about the journey this water has taken. These molecules formed in the outer regions of an alien planetary system billions of years ago, then spent eons frozen in the deep cold of interstellar space. Now, as our sun's heat begins to warm this cosmic ice cube, we're getting our first taste of alien chemistry. The water ice discovery had profound implications. Most interstellar objects lose their volatile compounds during the violence of ejection from their home systems. The gravitational chaos that launches comets into interstellar space often strips away the most interesting materials, leaving behind only rocky cores. This object somehow survived that process with its water ice intact, creating a natural cryogenic preservation system. The amount of water was staggering. Early estimates suggested the comet was ejecting between 0.3 and 4.2 kilograms of material every second, much of it in the form of water vapor and dust grains. That's like a cosmic garden sprinkler operating at the scale of Manhattan, releasing ancient water that had been locked away since before our solar system existed. The infrared observations also revealed something unexpected: silicate grains, roughly 10 micrometers in radius, mixed throughout the water ice. These tiny particles represented dust from the original protoplanetary disk where this comet formed, like finding ancient pollen preserved in amber. These microscopic relics carried information about the chemical composition of an alien star system. The detection of these chemical signatures raised tantalizing questions about the potential for even more exotic compounds. If water ice survived the billion-year journey, what else might be hiding in this cosmic time capsule? Carbon dioxide, methane, and even complex organic molecules could be present. Each new observation promised to reveal more secrets from this ancient chemistry set. Astronomers realized they were witnessing something unprecedented: the real-time analysis of pristine materials from another star system. Every photon of light reflected from this comet's coma carried information about processes that occurred when the galaxy was young. This was truly a cosmic archaeology experiment, providing insights into galactic evolution that no ground-based telescope could ever achieve. By studying the chemical composition of this ancient wanderer, astronomers were essentially analyzing a sample from the early Milky Way. The amount of water was staggering. Early estimates suggested the comet was ejecting between 0.3 and 4.2 kilograms of material every second, much of it in the form of water vapor and dust grains. That's like a cosmic garden sprinkler operating at the scale of Manhattan, releasing ancient water that had been locked away since before our solar system existed. The infrared observations also revealed something unexpected. Silicate grains, roughly 10 micrometers in radius, mixed throughout the water ice. These tiny particles represented dust from the original protoplanetary disk where this comet formed, like finding ancient pollen preserved in cosmic amber. These microscopic relics carried information about the chemical composition of an alien star system. This water ice treasure came with a cosmic deadline that was rapidly approaching. The viewing window was closing faster than astronomers had hoped. The timeline was brutally simple: visible through September, hidden behind the sun from October through November, then briefly reappearing in December before fading forever as it raced back toward interstellar space. That gave the global astronomy community roughly 6 months total to unlock secrets that had been traveling between stars for billions of years. The most frustrating part was that the comet would reach its closest approach to the sun in late October, precisely when it would be hidden behind our star from Earth's perspective. This is when comets typically display their most spectacular activity, developing dramatic tails and releasing the most interesting chemical compounds. We would miss the entire show. Fortunately, the comet was not only in our solar system, but it was headed toward a close encounter with one of our nearest planetary neighbors, Mars. The timing couldn't have been more fortunate. While the comet would be hidden from Earth's view by the sun, it would be perfectly positioned for Mars and its robotic inhabitants to observe. NASA's Mars Reconnaissance Orbiter, MRO, which had been circling the red planet for more than 20 years, could provide additional observations. Its suite of instruments included spectrometers capable of analyzing the chemical composition of the comet's coma and tail. The data would complement observations from Earth, providing a three-dimensional view of this ancient visitor structure and activity. The Perseverance rover, exploring Jezero crater on the Martian surface, might even be able to photograph the comet with its camera systems. While the rover's instruments were designed for geology rather than astronomy, the close approach could make the comet bright enough to capture with long exposure images. The Mars encounter would occur at the exact moment when the comet was most active, heated by its closest approach to the sun, and releasing ancient materials at maximum rates. But from Earth's perspective, this cosmic fireworks show would be completely hidden behind our star's overwhelming brilliance. For 2 crucial months, our sun would become the ultimate cosmic curtain, hiding the greatest show in the solar system. The timing of this encounter raised intriguing possibilities for future mission planning, demonstrating that robotic missions could potentially intercept similar objects. The European Space Agency's upcoming missions to Mars could be equipped with instruments specifically designed to study interstellar visitors. The close approach to Mars demonstrated that robotic missions could potentially intercept similar objects, opening a new chapter in cosmic exploration. The spectroscopic investigation began immediately after the comet's discovery, with telescopes around the world turning their most sensitive instruments toward this messenger from the early galaxy. Spectroscopy works like cosmic forensics, analyzing the way different molecules absorb and emit specific wavelengths of light. Each chemical compound has its own unique fingerprint, allowing astronomers to identify materials across billions of miles of empty space. The X-Shooter instrument at the European Southern Observatory's Very Large Telescope provided the first detailed spectrum, covering wavelengths from 300 to 2,500 nanometers. This incredibly broad range allowed astronomers to search for signatures from dozens of different molecular species simultaneously. Like reading a cosmic library written in light, each absorption line told part of the story about this object's ancient origins. The initial spectroscopic results revealed a fascinating puzzle. In visible wavelengths, the comet's spectrum appeared remarkably featureless, resembling what astronomers call D-type asteroids. These dark carbon-rich objects typically show very few absorption features, making them notoriously difficult to analyze. The similarities suggested this interstellar visitor might have a composition unlike anything in our local solar system. However, near-infrared observations provided much more detail. The SPECS instrument on NASA's Infrared Telescope facility detected clear evidence of water ice features in the comet's growing coma. The spectral signatures appeared at exactly the wavelengths predicted for water molecules sublimating in the vacuum of space. This was direct proof that 7-billion-year-old ice was transforming into vapor before their eyes. The Gemini South Telescope's near-infrared spectroscopy revealed an even more intriguing finding. Silicate grains, roughly 10 microns in radius, mixed throughout the water ice. These microscopic particles represented dust from the original protoplanetary disk, where this comet formed billions of years ago. Like finding ancient pollen preserved in cosmic amber, these tiny relics carried information about stellar formation, processes that occurred when the galaxy was young. What the spectra didn't show was equally important. Despite intensive searches, astronomers found no clear signatures of hydroxyl radicals or cyanide compounds, molecules that are commonly detected in comets from our own solar system. This absence suggested either different formation conditions in the ancient star system where this object originated, or unique preservation processes during its billion-year journey through interstellar space. The spectroscopic analysis also revealed subtle clues about the comet's internal structure. The way different compounds appeared and disappeared as materials sublimated from the surface suggested a layered composition, with more volatile substances concentrated in specific regions. This heterogeneous structure told a story about the original accretion process in an alien planetary system. Future observations with the James Webb Space Telescope promised to reveal even more exotic compounds. The infrared capabilities of this space-based observatory could detect carbon monoxide, carbon dioxide, methane, and complex organic molecules that ground-based telescopes might miss, providing a truly comprehensive chemical fingerprint. This cosmic archaeology experiment was providing insights into galactic evolution that no ground-based telescope could ever achieve. By studying the chemical composition of this ancient wanderer, astronomers were essentially analyzing a sample from the early Milky Way. The detection of chemical signatures raised tantalizing questions about the potential for even more exotic compounds. If water ice survived the billion-year journey, what else might be hiding in this cosmic time capsule? Carbon dioxide, methane, and even complex organic molecules could be present. Each new observation promised to reveal more secrets from this ancient chemistry set. The infrared capabilities of the James Webb Space Telescope, for instance, could detect these complex molecules that ground-based telescopes might miss. This promised an unprecedented glimpse into chemistry from the early galaxy, a direct chemical readout of conditions that existed billions of years ago. The unique combination of its age, size, and composition makes 3I Atlas an unparalleled messenger. It is not just a comet. It is a pristine sample of the cosmos from a time when the universe was less than half its current age. The molecules of water ice, the silicate dust, the organic compounds, all condensed under conditions that no longer exist in our local region of the galaxy. This literally makes it a piece of the ancient cosmos, preserved in perfect condition by the deep cold of interstellar space. University of Oxford astrophysicist Chris Linted emphasized the significance. This represents material from a part of the galaxy we've never examined up close. Every spectroscopic measurement is like receiving a postcard from the ancient cosmos, written in the language of frozen chemistry and preserved by the cold of interstellar space. The fact that it carried such a substantial amount of water ice is also incredibly significant. Most interstellar objects lose their volatile compounds during the violent ejection from their home systems. The gravitational chaos that launches comets into interstellar space often strips away the most interesting materials, leaving behind only rocky cores. But 3I Atlas somehow survived that process with its water ice intact, effectively creating a natural cryogenic preservation system. This implies that the conditions of its ejection were specific, perhaps less violent, or that its sheer size provided an inherent resilience. This raises profound questions about planetary formation and other star systems, especially those much older and more metal-poor than our own. If this object represented typical debris from ancient stellar systems, what did that tell us about the processes that created planets around the galaxy's oldest stars? The answers would come from understanding the unique orbital path that brought this cosmic giant to our doorstep and its pristine chemical makeup. It provided tangible evidence for theories about how primordial materials condense in young star systems, particularly those that might form more icy bodies due to a lack of heavier elements to form rocky planets close to their stars. Asterisk. The orbital calculations revealed something that sent shivers down astronomers' spines: an eccentricity of 6.2. In the language of celestial mechanics, this number told a story of cosmic violence and billion-year journeys. Any object with an eccentricity greater than 1 is on a hyperbolic trajectory, meaning it's moving too fast to be captured by our sun's gravity. This visitor was breaking that threshold by more than 6 times. To understand how extreme this is, consider that the most elongated comet orbits in our solar system have eccentricities just slightly less than 1. Even the previous interstellar visitors were modest by comparison. Oumuamua clocked in at 1.2, while Borisov measured 3.6. This new arrival was in a league of its own. The hyperbolic trajectory told the story of the object's cosmic journey. Like a marble rolling through a curved landscape, it had been bent by our sun's gravity, but never captured. The mathematical curve described a path that swept through our solar system once and continued into the void forever. There would be no second chances, no return visits, no opportunity for follow-up studies in future decades. The trajectory also revealed the direction of the object's origin. Tracing the path backward through space and time, astronomers could determine that it arrived from the general direction of Sagittarius, where the galactic center blazes with the light of billions of ancient stars. The thick disk populations in that region contained exactly the kind of old stellar systems that could have produced this cosmic wanderer. The orbital mechanics created a unique viewing geometry for different planets in our solar system. While Earth would lose sight of the object, other worlds would have front-row seats to the cosmic show. The hyperbolic nature of the orbit also explained why the object was accelerating as it approached the sun. Like a cosmic skydiver falling toward our star, it was converting gravitational potential energy into kinetic energy. The closer it got, the faster it moved, reaching a maximum velocity of over 200,000 miles per hour at its closest approach before slowing again as it climbed back out of the sun's gravitational well. After billions of years of wandering through interstellar space, this visitor would spend just months in our cosmic neighborhood before returning to the dark between stars. The controversy began when Harvard professor Avi Loeb, a physicist known for his provocative ideas, published a paper suggesting that the object's unusual characteristics could be consistent with a technological artifact. Loeb's hypothesis, which he had also proposed for Oumuamua, was based on the object's size, speed, and the peculiar timing of its perihelion passage. At 7 miles across and traveling at incredible velocities, this object was far larger and faster than typical interstellar debris. Loeb suggested that such characteristics might be consistent with a technological artifact designed for long-distance space travel rather than a natural comet ejected by gravitational interactions. The timing of the perihelion passage was particularly suspicious in Loeb's analysis. The object would reach its closest approach to the Sun in late October, precisely when it would be hidden behind our star from Earth's perspective. This cosmic game of hide-and-seek would provide perfect cover for any activities an alien civilization might want to conduct unobserved by human telescopes. The scientific community's response was swift and largely critical. Chris Lintet from the University of Oxford called the alien technology claims nonsense on stilts, and an insult to the exciting work going on to understand this object. Dozens of astronomers pointed out that every observation so far indicated completely normal comet behavior. The spectroscopic evidence strongly supported natural origins. The detection of water, ice, silicate dust, and other compounds exactly matched what would be expected from an ancient comet formed around another star. The object's coma development, tail formation, and outgassing patterns all followed well-understood physics of sublimating ice in the vacuum of space. Daryl Seligman, from Michigan State University, emphasized that numerous telescopic observations demonstrated classical signatures of cometary activity. The object was behaving exactly like billions of other comets throughout the galaxy, showing no evidence of artificial construction or technological capabilities. Even Loeb himself acknowledged the speculative nature of his claims, describing the paper as a pedagogical exercise rather than a definitive scientific conclusion. The controversy highlighted the broader challenges of studying interstellar objects with limited observation time and data. The scientific method requires extraordinary evidence for extraordinary claims, and the available observations provided no such evidence for artificial origins. The debate, while scientifically unsupported, served an important purpose by focusing public attention on this remarkable discovery and emphasizing the need for more comprehensive studies of interstellar visitors. The discovery of 3I Atlas has revolutionized our understanding of interstellar objects and the galactic ecosystem. Before Oumuamua, the very idea of objects wandering between star systems was largely theoretical. Now, with a third confirmed visitor, and one as extraordinary as 3I Atlas, we are beginning to grasp the sheer abundance of cosmic nomads. This suggests that our solar system is not isolated, but is regularly traversed by material from across the galaxy. It opens up new avenues of research. How frequently do these objects pass through? What is their typical composition? And how might we detect them more effectively in the future? This discovery has shifted our perspective from a closed solar system to a vibrant, interconnected galactic neighborhood. The questions this discovery raised extend far beyond its immediate scientific observations. It prompts us to consider how many other ancient comets pass through our neighborhood every year, undetected. Are they all water-rich like this visitor? Or do different regions of the galaxy produce interstellar objects with varying compositions, reflecting the diverse conditions of star formation across cosmic time? Perhaps most profound were the temporal questions this discovery raised. This comet had been wandering through space since before Earth existed, a silent witness to galactic evolution that spanned cosmic ages. What stellar explosions had it observed? What planetary systems had it passed? What cosmic catastrophes had shaped its long journey through the void? Its very existence is a testament to the incredible resilience and longevity of cosmic material, capable of surviving billions of years in the harsh vacuum of interstellar space. The legacy of this encounter would extend far beyond the scientific papers and conference presentations it generated. This visitor had demonstrated that the galaxy contains countless time capsules from its ancient past, floating through space and occasionally offering brief glimpses into cosmic history. Humanity's first detailed study of such an ancient object marked a turning point in our understanding of the universe's deep history. We were no longer limited to studying our own solar system's 4.6 billion-year timeline. The cosmos had hand-delivered a sample from its youth, reminding us that we are part of a much larger and older story. The questions this visitor carried back to interstellar space, its ultimate fate as it journeys out of our solar system and back into the cosmic void, will inspire future generations of astronomers. It will drive them to build better telescopes, launch more ambitious missions, and continue humanity's eternal quest to understand our place in the cosmic order. The brief, intense observation window for 3I Atlas has left us with a wealth of data and an even greater abundance of new questions, pushing the boundaries of what we thought possible in interstellar archaeology. It reminds us that the universe is constantly offering up new surprises, and that the biggest discoveries might just be hurtling towards us from light years away. Thank you for watching. See you again.